Okay, so we're used to, from this morning, thinking about like, how do you translate evidence from specific context into like a general understanding of what something does that you could maybe like extrapolate across contexts, like with the appropriate amount of uncertainty. So my job market paper, what I was interested in is like, what about when you don't think the average treatment effect is a very useful object, and in fact you don't think there is any kind of like useful average treatment effect that you could compute, and that you're really interested in distributional effects. So one reason why that might matter is if you suspect that the average treatment effects are extremely heterogeneous themselves. So in particular, if you think your intervention might be hurting some people and that the people it helps at the expense of other people, you need to know that. And, you know, so I think that's very important. I think there's also other kind of like social welfare reasons to think that the dispersion of outcomes, like just the raw variation that you see in people's incomes and consumption is like probably going to enter a reasonable social welfare function. Like societies that have more inequality and those sorts of things probably have different outcomes and different welfare. So what I'm going to do is try to handle that case in the Bayesian hierarchical setting for microcredit. So microcredit, I think, is a case in point of this issue. So you get these like kind of noisy small effects that are close to zero in this literature. But if you split it out by the quantiles of the outcome, so this is basically what you would get if you did that in Morocco, for the Morocco RCT. So here we've got the effect on the 10th percentile, the effect on 25th, all the way up to the 90th. This is not the effect on the individual that happens to be located at this percentile in the groups. This is the way that that percentile is changed between the treatment and control groups. So just literally, if I take the two CDFs, and I look at these percentiles, what's the additive difference in those percentiles? So what you can see in this case is that this sort of noisy zero is clearly a composition of a negative effect at some points and a positive effect at some points. And in fact, this distribution is spreading out, is being stretched out. So some people in this society are experiencing more positive results than they had ever experienced in the absence of microcredit, and some people are experiencing more negative results than they'd ever experienced in the absence of microcredit, and this society is seeing more inequality ex post. But this is just one site, and not all of the sites look like this. Not all of them display this negative tail. In fact, this is the cleanest estimate of a negative effect in the whole literature in any quantile. A lot of them do something like this, but you know, a lot of them are crossing zero or pretty noisy. So what we want to know is like, what's the typical impact that microcredit has on the quantiles of these sorts of outcome distributions, and whether this is going to replicate across different settings. Like, therefore, can we extrapolate to a similar setting? You know, should we be concerned about this pattern or another pattern that we see? But of course, we know it might not be possible to make any kind of robust or useful extrapolation across settings, and we talked about that. And I talked about why Bayesian hierarchical models are good for that. But there were no models in the Bayesian hierarchical framework to deal with these distributional effects. Thinking about just the difference between two CDFs is the continuous kind of version of the set of sort of quantile treatment effects. These are obviously transposed, but so that thing, whether you think of it as continuous or discrete, we did not have a way to aggregate that. And that's difficult. It turns out it's difficult to do. So I did the best that I could, given that I had to go on the market. And I think there will be a lot more, I hope there'll be a lot more work in this area, because I think that at the end of this, I was much more convinced that this is very important than I was at the beginning, which has not happened in other projects that I've done. Okay, all right. So I'm going to deal with two cases that need to be dealt with differently. So the one is, you know, when we were talking about that upper level of the model, or lower level, depending on how you think about it, the sampling error. We were relying on these asymptotic approximations to say, I kind of know how these sampling errors behave. And then we would draw some long bow to say, well, and also unmodeled heterogeneity within site is kind of governed by something like that. There are similar results for quantiles. We know stuff about quantile sampling variation. You can build models like that for quantiles that apply to continuously distributed outcomes. and then you can aggregate in that space. But it turns out that if you want to include data that's not continuous, then we don't have sampling results. We don't understand very much about the sampling variation in the quantiles. And we need to move to parametric solutions at this point. Okay. So what's difficult about extending the model that I showed you this morning, that Rubin 8 schools model, to this problem is that sets of quantiles, even if you discretize this sort of difference up and you look at these sets of quantiles, these objects are related to each other and contain a lot of information about each other. So if you think about just the raw knowledge of the quantiles of a distribution, if you know the value of the 50th quantile, and you know the value of the 55th quantile, you know a lot about the value of the quantiles in the middle. They have to lie in that region. Now, challenging, you don't actually know the quantiles, you're estimating them, but you still are getting a lot of information. And so you need to pass that information across the quantiles from an efficiency perspective, because otherwise you're leaving information on the table. But more generally, in this case, the information is a logical property of the estimand. And so if you don't pass that information or impose that constraint, you might end up with a violation of the property of the estimand ex post, which is going to be bad. So what I'm going to do is pass information across quantiles and impose that constraint by using variable transformation on the unknowns, which is very straightforward in a Bayesian framework. But then we're going to have this additional issue where if you want to work with discrete or partially discrete outcomes, the method that I use here will not work. And so then I have to move to parametric models. So this, I think, mostly at this point in the talk and when I was working on the project, seems like this kind of sad cop-out that you have to move to parametric models. And I think like the big surprise of this paper to me is like, actually the parametric models tell you like so much more than what you were learning from this other stuff. So like almost I think everything that we learned from this paper comes from the parametric models. And that's what my referees think too, and they want me to like move part 1 to some appendix. Which is shocking to me, absolutely shocking to me. So there we go. All right, so when we look at microcredit, I'm looking at 6 household outcomes. So I've got the household's business profits, their revenues and business expenditures. I have their consumption, their consumer durables, and their temptation good spending. This is alcohol, cigarettes, sugar, whatever. So what I find is that even though I use these different methods, and actually within the parametric models, I do a couple of different ones, what I find below the 75th percentile of these outcomes is a precise 0. And it's generalizable. So almost all of these sites are just giving you 0 all along that distribution most of the time. But then above the 75th percentile, there's a big variation within and across sites. So what's kind of interesting is that the generalizability of these effects is actually different at different points in the outcome distribution. So that I think is interesting. So we actually know what will happen if you introduce microcredit to, the distribution below the 75th percentile is not going to change. But above the 75th percentile, I cannot tell you what will happen. I do not know. Yeah.
One thing I was wondering about from before as an alternative to quantile regression. So you said you talked about CDFs.
Yeah.
I'm sorry, distribution regression would seem like potentially an alternative. But...
Yeah. So I could not make that work, but the reasons for that might have been, I think, kind of technical. But yeah, so let's talk about that kind of offline. But I do want to talk about that, especially because I was asked about it recently by another person who has substantial power over what happens to the paper. Okay. But part of the story here is that business data has very fat tails. In fact, what I'm going to show you is that the average treatment effect analysis not only is not giving you what you probably are really interested in, but is not even really coherent in this setting. It's not informative. It's super sensitive. It's very non-robust. And the Gaussian approximations on which most of frequentist econometrics is based are not reliable in this data set. So that is the sense in which that distribution that we are all assuming comes for free, I think, is actually more problematic in this setting. And then this is my pitch for you should think about using these methods. I think they're important, and you shouldn't assume your data satisfies Gaussian asymptotics because you might get a bad surprise. Okay, so I want to talk a little bit about the data in context very quickly because I didn't do that this morning too much. and then we'll get into the methods. We won't even have to talk about the average effects models. We'll just go straight to quantiles. All right, so I used a pretty a selection criteria, a set of selection criteria that in some ways were broad and in some ways were very narrow. So I only wanted to look at randomized controlled trials because I didn't want to think about the observational study issue. I just was like trying to abstract away from it. I don't think this is optimal to do, but this is like the easiest thing to do when you get started. I wanted to look at interventions which expand access. That's the policy conceptually that I have in mind. But within that, it can be expanding it pretty broadly defined, right? We've got studies here that are like, the treatment is we're building a branch of our MFI in your village. That's the treatment. But there's other studies here where we're pre-surveying people, and we're building a branch, and we're holding a meeting, and we're coming to your house, and some of the studies where the randomization unit is individual, we're dealing with groups of people who previously said they'd be interested in microcredit. And some of them, in one of the studies, it's even a group of people who had applied. So these are quite different groups of people and quite different kinds of expansions, and I'm just putting them all together. Yes?
I know they asked people. This morning you said something like you didn't want to look at studies which like added women, whereas they typically like provided the thing to men. So why isn't that access in like the same? Like why isn't that expanding access in the same sense?
No. So it's not that those previous studies were adding women; they were substituting away from men towards women. Yeah. No. So that's not expansion. This is all expansion. These are all sets of borrowers and communities who, in the absence of this stuff, are not getting any credit from these guys. Yeah. Okay. That leaves me with these studies. There is a risk of selection bias of study sites because there's conditions that you need to perform an RCT. I'm going to do what Ava does and restrict interpretation of generalizable to the set of like comparable sites. So the thought experiment is like, what would I see next time I do an RCT? I do think that's an issue. I think there's potential issues there, but I think it is a lot of work, and it turned out to be a lot of work to actually try to make traction on that. So I think we will have something for you, but definitely not today and not in the next 5 months. Yeah. Okay, so all 7 of these interventions are supposed to be relaxing a credit constraint, but we're dealing with a lot of dimensions of heterogeneity. So we want to use some kind of random effects or hierarchical model in this setting. And then this is my argument that, like, you really want to investigate distributional effects when the underlying RCTs that you're using have found evidence of heterogeneity across the quantiles. You've got a lot of economic theory that suggests you're going to have winners and losers from these kinds of interventions. It's also plausible that the people who lose are the poorest people already from that theory literature, the least financially savvy and poorest people. So therefore, you've got to be worried that you're going to affect inequality across households. That seems like a potentially bad thing to do to a society. There is also this like nice thing where maybe actually households use microloans to adjust risk exposure, and that could be a good thing that microloans do. That will not change the average outcome. That will only change the dispersion in the outcome. So that's another reason to look at beyond averages. Okay, so this is literally the teaching slides I give everybody. Then that's what Ava told you guys about. Okay, here we go. So that usually takes 30 minutes. All right, so quantile function is an inverted CDF. Conditional quantiles, so modeling the quantile of a distribution, conditional on some other variables, are very ugly objects, except if you only have a single covariate of interest, a binary treatment assignment indicator. Then this is a very easy problem. Because in that case, the conditional quantile, if I just say, I've got an intercept and a slope, the intercept is just the value of the control group's distribution at that quantile, and the slope is just the additive difference between the treatment group's quantile value and the control group's quantile value. And that's because this model is saturated, so it can't exhibit all the yucky things that other models exhibit that are not saturated, like Quantile Crossing, in its raw form. Okay, so we care about this vector of quantile treatment effects from the 5th to the 95th percentile. As a practical matter, don't go above the 95th percentile because extremal quantiles are very hard to work with. Even the 95th is difficult, but like, yeah, that's all of Victor Chernizhikov's like early first decade of work is like extremal quantiles, stay away from them. Okay. So why are quantile treatment effects the right metric? Because sets of quantile treatment effects capture any difference between the distribution functions of the outcomes between the treatment and control group. Now, I want to make it clear, the thing they don't capture, which is not on the slide, because usually they have an adversarial audience, is they don't capture any difference between what people's outcomes are, right? People could be swapping around in the distribution and you will never see that, okay? But as a policymaker, unless you know a lot about who's swapping where, then you don't need to be so worried if people are just swapping around. In fact, like, there's another literature that says it's good if people swap around. We want people to swap around in the distribution. That's what social mobility is. But if you're interested, as I am, in this idea of like, if the shape of a society's, say, profit distribution across people is changing, I think we can make statements about whether we like those changes or not in the aggregate. Whether we think it's good for societies to have profits concentrated in the hands of a few people or not. Whether we think it's good for consumption to be concentrated in the hands of a few people or not. So I want to contrast this to my main competitor, which is subgroup analysis, models that interact treatment with covariance. So if you're going to find heterogeneity using those methods, you need to have the right covariates. So you better hope that you can measure the thing that determines the heterogeneity, and you have to enter it in the model correctly, right? You have to get the functional form correct. So I think that's not always clear that we can do that, especially because the covariates themselves might need to be interacted, right? So it's not men or women that have different effects. It's women over 40 have positive effects and men under 18 have negative effects or something like that. They need to interact all this stuff. It's going to be ugly. Also, if interventions affect people's risk-taking behavior, there are no covariates that predict those differences. That's the definition of risk. So quantile effects can find that, which is good. They're also more robust as statistics and have limited researcher degrees of freedom. Yes?
Just one thing about so sometimes people worry about like a fraction of the population that is hurt by the treatment. We do care about whether people are swapping. Typically,
that's true.
You have negative swaps.
Yeah, that's true. Oh yeah. Do you want to like briefly say that again for the live stream people?
Yeah. So just 1 point. So under some social welfare functions, you might care, for example, about the number of people who are hurt by the treatment. And when you have a lot of swapping of quantiles, then you may have you often have a lot of negative effects.
Yeah, so I think, yeah. So you're totally right that if what you care about is like absolute number of people who are hurt, and you don't care about like making that net by subtracting off the number of people who are helped or anything like that, then yeah, this is not going to give you that. But if you did want to make it net, you can start to get back to it. Like this is going to, if people are canceling each other out, you won't find them. If they're not canceling each other out, you will. But also like, yeah, I think that goes in that general bucket of like, there's absolutely things you can't learn from quantiles, but you're not guaranteed to learn them from subgroup analysis anyway. Yeah. Okay. So we've got these two problems. If you want to do naive quantile set aggregation, you got to so naive quantile set aggregation, sort of hard to define actually, because depending on who you are, your first instinct would be quite different on this problem, I think. But if you don't pass information across quantiles, you're going to have problems. And if you don't deal with the fact that quantiles are weird objects when the data is discrete, you're going to have problems. All right. So I've got this set of quantile treatment effects. It's a 10-dimensional vector that just tracks these differences between the treatment and control CDFs. And I have k of them. And I'm trying to get from this, set of k different estimates to a notion of like, what's the average difference in the quantiles of this outcome distribution across this set, and what's going to happen next time to this outcome distribution. But of course, we also need to know the variation in the set of quantile treatment effects, which is now variance-covariance matrix. So we want to build a hierarchical model. We need to pass information across the quantiles. if we don't, we have a risk of violating the monotonicity of the underlying quantiles. So it's not that the effects have to be monotonic, the underlying quantiles have to be monotonic. So that is the constraint that we are worried about. If you don't enforce that constraint, you might end up predicting a set of quantile treatment effects which are not logically compatible with the underlying data that you have. So that's not good. So some people seem to find it palatable to use estimators that can violate monotonicity or other things like that. If you're one of those people, Viktor Chernizikov has a paper for you that says, in general, imposing monotonicity gets you uniformly closer to the truth. Now, he's not working on quantile crossing in this context. He's working on the general quantile crossing problem. So quantile regression can exhibit this problem if the model is not saturated, even within a data set. Just because of how the approximation is done. So even in that setting, imposing monotonicity gets you uniformly closer to the truth. So that's good. Okay, so I know from the work of Frederick Mosteller that actually sets of sample quantiles have an asymptotically Gaussian sampling distribution. And we actually know what the variance-covariance matrix looks like. From his work. So that's pretty cool. So then the first thing you might do is use that theorem to build a multivariate version of the Rubin model that I showed you, and that's the first thing that I did. But it turns out that this model can violate implied monotonicity, even if you directly apply it to monotonic vectors. And the reason for that is not extrapolation error or issues with the asymptotic approximation, but because of how averages work. So averages of monotonic objects need not themselves be monotonic. The property doesn't follow through, unfortunately. So let me show you how this can happen. So think about these as estimates of the quantiles of distributions in site 1 and site 2. And site 1's values lie above site 2's values in the y-axis. But site 1 is very uncertain at the top. By contrast, site 2 is quite precise at the top. So what's going to happen is that curve 2 is going to pull the top down. So you're going to get a non-monotonic average. So this is a quantile crossing problem. So what Chernizikov and co-authors would say to do in this setting is to rearrange the function. So you take this point over here, which this logically impossible value, right? So that can't be the right point estimate. You move it over here, where it could be logically admissible. But there's lots of other things you could do. You could iron the function. You could project the function. So I'm going to take a little bit more systematic approach and say, I'm going to work in the space of monotonically increasing functions. That's the space I'm going to work in. I'm going to solve the whole problem in that space. And then we're going to get the answer only inside that space. Okay, so since the underlying quantiles are the things that have to be monotonically increasing, they define the constraints on the beta 1s, and they need to appear in the model. So what I'm going to do is, right now these quantiles are just like 10-dimensional vectors that live in R10. Okay, so they're not constrained to be monotonically increasing. What I can do is transform those variables into 10-dimensional vectors that are constrained to be monotonically increasing. So specifically, the transform that I'm using is I'll use the raw value of the first entry and the log differences of the additional entries. So that thing must then be monotonically increasing. Now, of course, in classical frequentist econometrics, working with transforms of parameters is very ugly. But in Bayesian inference, all unknown objects are random variables. Transforming random variables is very, very easy as long as the transform is well-behaved and one-to-one, like a log. So we transform Q1 to a monotonic vector that restricts the support while preserving all the posterior uncertainty. So now we're searching around in this space for the right answer, as opposed to ex post rearranging or ironing or something like that. So that's nice. So that's what I ended up doing here. This is really like a very similar model, except I'm imposing monotonicity. I also want to point out, so I'm shrinking here. The reason I'm not doing it jointly, that you saw before I was doing joint mu and tau, this is because of computational problems, right? So each of these is a 10 by 10 matrix. If I want to allow this thing to be joint, this is a huge matrix. So I'm not interested in solving computational tractability issues. I hope somebody else will do that, but so what I've done is just aggregate them independently for now. So you need to also aggregate the beta zeros, which is just the control group's distributions, this Y0 distribution that Michael was talking about. First, because that defines the upper level constraint. So you need that object to exist, this beta 0. But secondly, because it tells you something about how to interpret the results on beta 1. So if you find that your beta 1Ks are all close together, so you get a lot of pooling and you can say a lot about what the next beta 1K will be. So sigma 1 is small in some sense. So that's good, except if I told you that actually the beta 0Ks are all close together and sigma 0 is really small, that means that I studied really similar places. And so maybe the reason why I see similar impact is because I study similar groups of people. On the other hand, if sigma 0 is huge and the beta 0Ks are completely spread across the space, but I still get a lot of pooling on beta 1K, what that means is that I'm learning something that I can actually transport across disparate types of control groups, and that's exactly what we find in microcredit. So you plug in the control group quantiles into the hierarchical model, it spits out the same numbers that you plugged in. It does 0 aggregation on the control groups, but it does about 60% aggregation on the treatment effects. So that's cool. This is boring stuff about pooling metrics, which probably don't work very well. Okay. I think Ava outlined all the issues and I didn't solve any of them, so. Okay. So the previous method was built on this asymptotic sampling theory of the sample quantiles. And it's sort of nice because, that's kind of works for any continuously distributed outcome. It's a non-parametric kind of result in some sense. But it only works for continuously distributed variables. And in applied economics, not every variable is continuously distributed. And we're not just talking about okay, things are measured in dollars and cents, right? So everything is measured in USD PVP. The consumption variables are still kind of fundamentally continuous. You have to dither them a little bit in some parts, but they're continuous. The problem is that the business variables are deeply non-continuous. They're mixture variables. So let me show you. This is the profit data for India. This is a stacked histogram. There are actually people in the treatment group in the spike, but I had to truncate the spike. If I didn't truncate the y-axis, all you would see is a vertical line. It's about 30% of the sample. It might even be a bit more. I also had to truncate the x-axis. So the tails are thinner than this, or are wider than this, sorry. So if you look at this, this is not a continuous distribution. We're in big trouble for quantiles. But this graphic actually tells you the whole rest of the paper. So if you've ever seen any power law distributions, these tails are extremely heavy. This is not data that is going to converge to asymptotic, Gaussian in any kind of reasonable sample, and maybe never. So actually, that's the whole result of the paper is if you just graph the data, you'll know what you're dealing with. But okay, so what if you just try to apply a theorem even when you shouldn't apply it? It's not good. So here is if you did the quantile treatment effects on the Mexico profit data using the theorem, and below is if you do a non-parametric bootstrap. Okay, so the fact that these things don't agree is bad news for at least one of them. But in this case, the bootstrap's also doing poorly. It actually thinks that the standard errors are 0 here, which they aren't. This is a sample from a group of people. It's not 0 standard errors. Bootstraps actually also require some kind of continuity, unfortunately. So what I'm going to do is I'm going to parametrically model the distribution of household business outcomes using richly parameterized mixture models. And then I'm going to aggregate by placing a hierarchy on top of that model. So basically, you have to use contextual and prior knowledge about why your data has that shape or what's a good way to characterize the weird shape of the data. But if you're willing to do that, it solves all the problems that I described before, because if you build proper mixture PDFs, they integrate to proper CDFs that are monotonically increasing, and they pass information across quantiles. As far as I know, this requires the full data. So the reason why it makes sense to do this is that so as soon as you have a weirdly shaped distribution, you start to think about mixture models, but it's very hard to deal with these partially discrete mixture models. So I was talking to lots of statisticians and computer science people about it. And eventually I had this conversation where one of them said to me, it's a real shame that you don't know that the spike will always be at 0. Because if you knew where the spike was, then you could just make this mixture model with these non-overlapping components, and then that's easy to solve. And I said, no, I do know that the spike will always be at 0. This is a profit distribution. It would be insane if the spike was somewhere other than 0. Think about the sampling process and think about the decision process of the people in this sample. So we're sampling poor households. We don't sample business owners or business operators. So in poor households, their business profit that you measure is the outcome of a partially discrete decision process, right? So there's an extensive margin decision. In fact, there's 2 extensive margin decisions. First, I have to decide whether to own a business. Then I have to decide whether to operate it, right? I don't operate my business every period. A lot of people in these samples are in seasonal agricultural labor or something like that. Once I decide to do that, then I get sent into the tail of this distribution, either positive or negative, depending on what's going on with me. So that's a pretty coherent story. It's not hard to build a model that describes that. And you can build that model just using statistics. Of course, you could also build it using economics, but statistically, a mixture of 3 distributions, one for the lower tail, one for the spike, one for the upper tail. And then you can just allow microcredit to affect allocation to the different components, as well as the shape of the tails, right? So we have the ability for microcredit to affect all these aspects of this complicated distribution. We can also use our prior knowledge that things like wealth, profit, and income tend to follow power laws. So we can use, for example, a Pareto distribution. And because, again, quantile treatment effects are just transforms of this underlying stuff, right? So I'm going to let microcredit affect the scale parameter of the Pareto and the allocation between the spike and the tails and stuff. But the effect on the quantiles is just an analytic transform of that, so I can recover that completely and all the uncertainty in the Bayesian framework. So that's nice as well. So here's an example of what that would look like. So here I have 3 weights, the big lambdas, because of the 3 components. Those are affected by your treatment status via a multinomial logit model. And then once you're in one of the tails, you're distributed according to this Pareto distribution. And then here treatment affects the scale parameter via this parameter kappa. And then I can aggregate, everything's going to be in log space because a lot of these parameters can't go below 0. And that makes everything kind of easier. Okay, so the problem is that if you're going to parametric models, you need to do a bit more model checking. In fact, you should always be doing model checking, but this is... You won't, if you're wrong when your model is like standard, at least you're wrong in company. If you're wrong when you like build some crazy model, it's very lonely out there. So then you might want to do some kind of model checking. So I have this bullet point that I keep meaning to change because I say that good fit means you're probably not wrong. I think that's not a good way to say it. I think that's not true. A better way to say it is if the model fits the data really badly, you might want to get a better model. Like, you know, if you're off by like several orders of magnitude, you probably want to get a better model. But of course, if the result is robust to the model that you use, then it doesn't really matter if you're wrong. So that's kind of fine. So in the microcredit data, what I did is posterior predictive analysis, which basically says how good is the model at predicting the data I already saw. Slightly controversial metric. But it turns out that in this metric, the Pareto fits badly, and actually a log normal fits better. So that's kind of interesting. They both give you, however, the exact same qualitative story. You get this precise 0 across all the sites, and then you get this kind of tail that's going all over the place. Yeah. All right, so this is what you get on consumption. So the red one, so the line is just like the point estimate. The red central bar is the central 50% posterior interval. The light colored bar is the 95% central posterior interval. So that's what you get on consumption. That's sort of what I promised you. If you did this full pooling kind of quantile analysis, that's what you would get over there. So I think at this point, it's fair to be like, that was a lot of work for an answer that looks pretty similar. But the real difference, like this is only 55% pooling. Now, it's hard because when I'm saying it's 55% pooling, I had to make a call on how to average across the quantiles. I made the best call I could, but there's so many issues with these pooling metrics that, you know, but so regardless, like there's quite a bit of pooling here, but it's not close to 1. And the way you can see that is if you look at the prediction for the next site, there is substantial uncertainty, particularly in the upper tail. In this setting, it's, you know, even though you get 55% pooling or some, you know, good amount of pooling, that prediction on the next setting is really going to be affected by the model that you use. And I think this is much more appropriate. Okay, now we got profit. So profit's quite interesting. So here, the point estimate down the bottom is actually 0, and 50% of the mass, actually more, like 75% of the mass is like stacked on 0. So there is this lower tail, but you know, this model is pretty sure that nothing happens most of the time down there. Not as sure as with consumption, where it's really sure, but it's pretty sure. There is this wobble in the top, so it looks like there's some evidence that something's happening in the top. Now, this uncertainty interval does cover 0, if that matters to you. I would say this is like pretty strong evidence that something is happening in the top, but not generalizable evidence. And in fact, if I give the prediction for the next one, you're super uncertain what's going on at this top. You're also like, you know, so one of the reasons why this is uncertain is because I think only one site finds that. It's actually only Morocco that finds that negative effect, but it's like the most precise effect. So it's very hard for the model to know what to do in that setting. And that's what you're seeing here. So what you can see is if you did full pooling in this case, you're going to be substantially overconfident. So this is not a good situation. So why is that happening? So part of the story is that in this data set, the log normal variances in the Pareto scale parameters imply extremely heavy tails for the business outcomes data. So the log normal variance will tell you what the excess, well, combined with the mean, but the mean is like a much smaller role, will tell you the excess kurtosis of the distribution. So these distributions have an excess kurtosis of more than 800. Just for your reference, like an excess kurtosis of 8 is about when the median becomes more efficient than the mean. Okay, so we're well into that territory, right? A median's a much better estimator of the location of this distribution. The Pareto scale parameters actually imply such heavy tails that this generating distribution doesn't have a finite variance and doesn't have a finite mean. So you can, if you don't like to think of that literally, just think like adding or removing one data point will drastically change the mean of this distribution. So that's really bad. Formally speaking, if you don't have a finite variance, you don't have a central limit theorem. And if you don't have a finite mean, you certainly don't have a law of large numbers. In practice, what that means is like samples of like hundreds of millions are still going to be unstable. So that's not ideal. But this actually does happen in economics data. So Mandelbrot actually worked on this. So we have our second celebrity mathematician for the afternoon. Gene Farmer found that this is true in financial returns. Financial returns data don't have means. Xavier Guébet has a fantastic paper on this if you're interested. Aaron Pancost, his job market paper estimated the productivity distribution of Indian firms. It doesn't have a variance. And Sam Bazi estimated the distribution of land holdings in the Philippines. It also does not have a variance. So, like, in fact, I have not seen somebody use a Pareto distribution that did turn out to have a variance. So I would be very interested in more work along this line, because I think that fat tails are much more common and much more problematic in economics than they appear. And so, you know, some people want to trim to get out of this problem. I don't think that's a great idea either, because if you do that, like, yeah, the mean of the trimmed sample is going to be more stable. Although, let me say, like, you have to trim more than 5% out, right? Because I'm doing the 95th quantiles. You have to trim more than 5% of the data out. But from an economic perspective, if you go into these Indian villages or, you know, these guys in rural Philippines and you trim out the top 2%, and then you study what's going on in those groups, there's like trying to study the US economy and trimming out Apple and Google and Walmart and Bill Gates and, you know, everyone else. So you're not really going to understand the group of people that you're studying if you trim out these people or these groups of people who are at the top. Yeah, so I think that's kind of very serious. But also, you know, I think part of the reason people want to trim is because they'd like to ignore the problem. But it's actually not that hard to compute a median. Like they're not like beautiful. They're not the result of calculus, so they're kind of ugly. But like, it's not that hard. So like just reporting the median is going to get you, or like some other central quantiles is going to get you a lot of the way to understanding this stuff better than like trimming stuff out. Okay. All right, so let me discuss a little bit what I think the bottom lines are. So it looks like, oh yeah.
Two questions. I guess so. One is that often why people trim is that they're worried about measurement error. So that's one thing. And I guess the other thing was, I was just wondering whether, so what's happening is you're aggregating across the parameters of this mixture distribution, right? And so do the sort of individual or the posteriors you get for those parameters, are those, so in some ways, like, I feel like what you've shown us is like a summary statistic, kind of thinking about all the parameters at once. But I'm wondering if you think there's something illuminating from an economic perspective about the parameters themselves.
Yeah, so let me answer that and then go back. So I did, and I think do think that there's something illuminating about knowing, like, well, things are more happening on like pushing people out of the spike and into the tails, or things are more happening in terms of like switching between the tails, or the shape of the tails is changing. And I used to make a big deal out of that, and then Steve Pischke sent me like an example of how like a bunch of stuff could be changing on those things, which you then like would cancel each other out in a way that you wouldn't see, but then would like show up in in like the summary statistics. So like, no, he had the opposite. So he had like a pattern that you would then interpret as if it had made some big impact, but actually it was like a trivial kind of So unfortunately, it seems like there's some argument that these underlying things may not be so useful. To be honest, like I can't say that I deeply understood the point he was making. Like, so I don't think I'm fully convinced that it's not illuminating, but I definitely haven't spent the time trying to figure that out, because it doesn't seem to be like the fight to have right now, I guess. But I do think it's in principle interesting, and I'm not really sure why it wouldn't be identified. Like, the model's identified, I'm not really sure why it wouldn't be identified. But I remember at the time thinking like, oh, this is a good example. I have to think a long time to come up with a counter argument. But of course now I can't remember the example. Okay, so measurement error. So I think initially when I was looking at this, people were saying this is measurement error. So what I find interesting about that is like, this is like a classic fat-tailed distribution shape. So like the whole thing is screaming that this thing is a power law, or some kind of very fat-tailed thing. So, you know, the argument people make about measurement error is they usually say like, well, okay, like negative 60 billion is a mistake, right? Sure, but like, I got like quite a few guys out here, like, and they're not like negative, like this tail is populated all the way along, sparsely, but populated. So, you know, and it's not that these numbers are all ending with like 6 zeros or anything. So to me, it doesn't look like measurement error, unless you think that the measurement error is contaminating the whole distribution. So that I think is hard for me to argue against. Like maybe this distribution is actually student T, and then there's some kind of Pareto measurement error, which is now like, that's what governs the whole shape of the thing. And the measurement error is now, you know, as a mixture, more than 50% of the distribution or something. So like, I don't think you can rule out that that is happening, except by saying like, it doesn't look like it. And we've now checked, so like, especially because it's business variables, I think that the measurement error argument is more concerning because it's very hard to measure business variables. But as part of a project on robustness that I have, actually with the same guys who are like, oh, what a shame it's not always at 0. Those guys, we started looking at this robustness metric for like, what if I remove like 5 data points, does it change the sign of your estimate type of thing? And we started looking at stuff that really shouldn't be fat-tailed and also shouldn't be hard to measure, like calories or like how much you spend on food every week. But even sometimes in those things, you see the shape. Those look more log normal, because actually, so the other point to make is that like the bin width of histograms is a tuning parameter. So actually, if you zoom in here and you break the bin width up more, you see there is a little hump here. So that is probably why the log normal is winning. And actually, like some of the feedback that I've gotten, which I will probably action, is like you should put log normal here and then cut it or something like that. But so I don't think it's measurement error. I suspect that this is a real feature of land holdings in the Philippines and profit in small businesses, and it's certainly a feature of financial returns in developed economies. With that said, like if someone could propose an interesting test, I certainly could be wrong. I would be interested in that. But yeah, it's true. I do also find it really interesting how often, like, economists who will fight you on the idea of like a prior on a treatment effect will be like, anything I don't understand is measurement error. So I find that quite interesting. I'm not at all saying that you were saying that, but yeah, which you were not saying. But any chance to make a Bayesian point, I will take. Okay, so what do I have? I have like 3 minutes. That's fine. Okay, so you might be thinking that precise 0 is because of the spike at 0, or because there's low relative take-up. So it's actually not just the spike at 0, because the consumption variables exhibit this pattern, and also the tail. If you just look at the positive tail, that exhibits the pattern. The low take-up is harder to deal with if you don't think that Sutva holds within a village, which I don't think it does. So I did a kind of pretty slapdash bounds exercise, and the bounds are super tight, suggesting that, like, you know, there's not a lot of heterogeneity between the people who take up and the people who don't, which is weird, but would also explain the 0 treatment effects most of the time. So, so that's kind of interesting. But so I don't think it's the spike at 0 or low take-up. And above the 75th percentile, the models really don't want to make general predictions. There's this high variation within and across sites. So this is the point where you think, oh, you've got so much variation, what if you could get your hands on some covariates? So we have some I could not even see how to do a 10-dimensional ridge regression, 10-dimensional outcome ridge, so I just didn't do it. But what you could do is use this household's prior business experience covariate, which is like the only pre-treatment covariate that every site collected, which is great. And what's interesting is when you condition on that, you don't actually explain the heterogeneity at all. You locate where all the heterogeneity is. It's in the group of people who have previous business experience. So if you have no previous business experience, basically nothing happens to you. There is a little wiggle in the top, but it's very small. All of this pattern is coming from the guys with the business experience. So I think that's very interesting. And there's more evidence that these guys actually are increasing consumption in the right tail. That is a tighter estimate. So I think that's interesting, but I still think it's very heterogeneous within that group of people. Oh yeah, and the point I wanted to make before is like, those of you who've played around with this microcredit stuff or other studies, you may notice that sometimes when you do RCTs, or sometimes when you do these regressions on these data, controlling for covariates, even really rich covariates, doesn't seem to explain much variation. That's because there is nothing that can explain this much variation, right? Like covariates don't vary enough to explain this. So that's like, you just can't do it. That's life when you got kurtosis. And without a rank and variance assumption, you can't go to individuals fine. So we did new Bayesian hierarchical models, which is exciting because we just learned them this morning. We had to solve some funky problems that seemed initially like econometric problems, but turned out to actually be economic problems, which I think is also interesting. The kind of point I want to make here is that quantile regression and parametric models are giving us new robust insights that we cannot get with linear regression done by OLS, right? So the parametric model has a lot of structure, but it's actually not nested by OLS regression, because OLS regression assumes that the mean is finite, right? But I can easily build, and I just built you one, a parametric model that does not make that assumption and still allows you to learn about what's happening. And so I think we need to get out of our minds this notion that like the more parametric the method is, the more unjustified structure it imposes and the less solid stuff we're learning. I do not think that is true. I think we can actually learn a lot more about the data that we're using if we're willing to give things like quantile regression and parametric models a shot. So thank you guys very much. There's a question.
Yeah, thank you for the presentation. Can you come back just a little bit on the low take-up idea?
Sure.
What have you, I mean, it might look a bit simple, but have you tried excluding the studies with the lower take-up rates and just keeping the ones with high take-up rates?
So let me tell you that story. So there's two studies that have a high take-up rate. They're the studies, not surprisingly, where there was more intensive pre-screening of the population. However, and so I used to make a big song and dance about this because they're not the biggest treatment effects at all. In fact, they are Bosnia and the Philippines, and Bosnia has like one of the smaller treatment effects, but more precise, and the Philippines has the largest treatment effect, but it's super noisy. So they're not like, there are different quantiles of their own distribution. Like they're, you know, so I thought looking at that, like that's kind of a slam dunk, right? Like these guys have like 80% take up. The other studies have more like 20 to 40% take up. To me, that seemed like a slam dunk. It's not low take up. However, one of my first set of referees pointed out, actually the relative take up in the treatment and the control group was about a 20% gap in all the studies. So like the control group people, and this is not just like any microcredit. This is like microcredit from that microlender. So the control group guys generally manage to get their hands on this stuff. So I think that is kind of interesting because on the one hand, we have like much lower take up in the treatment group than you'd think, but then higher take up in the control group than you would think. So to me, that suggests that like there's some other important process occurring here that is just not captured by what we're studying, and that microcredit, you know, is not the key lever. That like sometimes it's a useful input to something else, but sometimes not, and it's hard for us to predict it with what we. That would be my reading on this. Like, you could also tell like a behavioral story where like people just take up this stuff that's bad for them, but like. I don't know. I'm more convinced that like there's something else more important is happening, and microcredit is sometimes an accessory to that and sometimes not. That's my take on it, but like that is an intuitive take based on taking graduate development economics. Yeah. Any other questions? Yes.
For the inexperienced entrepreneurs, do you see the variance of their consumption decreasing with treatment?
So we don't have, we can't track the same people over time. We don't only, yeah.
No, no, actually.
But you mean in the cross-section?
Yeah, in the cross-section.
Let me try and remember that. Can I operate this? No? No. I don't remember. I think, there is an interesting story. No, so what you see is, it seems like they get a little more of this uptick in consumer durables. But like the whole thing is still close to zero. So it's like, you're kind of reading the tea leaves a little bit. In the like world of reading the tea leaves, like I don't see I don't remember seeing a decrease in variance. What I remember seeing is that, so hang on. So I remember seeing a slight uptick in consumer durables, but still very mild. And I think there was like a very slight downtick in the top of consumption. So that is technically a variance reduction. If you could like, but it looks like it could be a wobble. It could be, But then that looks a bit more like substitution plus reduction or something. Yeah.
Yeah, so not, I guess
Yeah.
I was more thinking about the low end of the distribution.
Oh
getting
yeah,
pulled
coming
in.
up. No.
Yeah.
No. Yeah. Still, the action is in the top. Yeah. It kind of sucks because what's interesting to me is sometimes people say like, well, consumption's bounded below by 0, so mechanically not much is going to go on there. It's like, that's not true. If you took the poorest people and you gave them more food, you would move that part of the distribution up. Like, yeah, you can't take stuff away from them. You can give them more stuff. Like, you could if the additive effect is if the average treatment effect estimated by these like linear additive models is telling you something like the whole thing should be uniformly shifting around, and it never is that I've seen. Yeah. Sorry, I went on a tangent. Cool. Thanks, guys.